So right here we have a simple thevening example, and they are giving us a combination circuit, and they are saying thevenize the circuit from this point. So from this point to the left, we are going to thevenize to see how this RL is going to see these circuits. So the first step before we move on to here is to remove the RL. We are not going to change anything from the RL. We're just going to remove, thevenize these circuits, and then replace or put back RL into it, okay? So they're giving us the solution, but I actually work it out. So let's see what it does. So we have our source, R1, R2, and RL gets removed. So the first thing is, when we are solving for R thevenin, so here is my equivalent circuit where I have removed the RL. So R thevenin is looking into the circuit from here. My eye is here and is looking into the circuit from here. So the first thing I did, R thevenin, is to remove RL. The second thing is to replace the voltage source by its equivalent resistance. So we said that if it was a voltage source, it was replaced by a short. So I shorted out, and now my R thevenin is just a parallel combination of R1 and R2. So I just do that and I get 7.30 kilo ohms. Pretty easy, right? Now I'm going to find my V thevenin. I reconnect the voltage source, and now I'm going to look voltage wise from this way. So if I pay attention closely, my V thevenin is nothing more but the voltage across R2. So now this is my V thevenin. Let's analyze the circuit. The circuit comes here, it goes this way, comes here. Can I split this way? No, it can only come this way. So therefore I only have a series circuit. So I do a simple voltage divider here, and I get that my result is 8.76 volts. So that is my V thevenin. So now I redraw the circuit where I have my V thevenin, I have my R thevenin, and I just place back, or I put back the R total, or the R load. So this is my equivalent circuit. So I go from here to here. Yes, you might say, oh, this is not so much simpler, right? But this is just a basic example, and the answer we can check with is 7.30 for R thevenin, 8.76 for V thevenin, and that is what they have right there. So it checks out. So let's move on. So Thevenin theorem. Like I said, we are supposed to be able to analyze the bridge and Thevenize it, and do a lot of different analysis into this bridge, because it's a famous configuration. So this Thevenin theorem is useful for solving the Wheatstone bridge. One way to Thevenize the bridge is to create two Thevenin circuits from A to ground, and then from B to ground. The resistance between point A and point and the ground is R1 in parallel with R2, and the resistance from B to ground is R2, 2 and 4 are parallel. The voltage on each side of the bridge is found using the voltage divider rule. Yes, I don't like that approach, so I worked it out with my own approach. So here is the example. They said Thevenize the bridge, and they are giving us the solutions and the values. So let me show you how I work it out, rather than doing it the way they are suggesting it. So right here, let's start. I draw the circuits. I have my R1, my R2, R3, and R4. Remember, I cannot assume the bridge is balanced. If they told me the bridge was balanced, then it's easy. I know the values of these points, and I know that the value here should be 0. But they are not saying that. They are not saying that, so I have to analyze it. So I have my RL. The first thing is to remove the RL and replace source by its equivalent. But before I do that, let me redraw this so it looks less scary. So I just make it all boxy so it's easier for us. So I know that I have to measure the voltage, the potential difference between this point and that point. So I'm going to redraw it. I remove the source and replace it by its representation. Then I say my R thevening is going to be between these 2 points. So how do I go here? Now this is where your chapter 4 and chapter 5 comes into it. You have to follow the rules. You have to find the nodes and follow the jumper wires, and that's going to simplify you a lot. So right here, I know that R3 is here, and I go across and it's connected to R1, but R3 is also connected to R1. So therefore, they are connected on this side and they are connected on that side. So they are what? They are in parallel. So R1 and R3 are in parallel because they are connected in 2 terminals. The same thing for R2. R2 is connected here with R4, and R2 comes here, cross, and is also connected here. So R2 and R4 are also in parallel. Then they are connected in between because R2 and R1 are also connected. So R2 and R1 are connected, but also R1 and R2 are connected from the thevening. So this is where these wires are coming for. So don't worry if you don't see all this redrawing. You're going to get it as you practice. The more you practice, the more you do circuit analysis, it'll come to you. So once I have it like that, it's easy, right? R thevening is just parallel combination of R1 and R3, and the parallel combination R3 and R4. So this is going to be my R equivalent 1. R1 parallel with R3, R equivalent 2 is R2 parallel with R3. No, R4, excuse me, R2 and R4. So I just R1 and R3, R1 and R3 as 330, both of them. So I can just divide it by 2 to get my equivalent. R2 is 390 and R4 is 330. So I cannot divide them. I have to use the formula. I get 178.75 ohms. So then I just do the equivalent circuit here, and then my R thevening is just the series combination of the two. Why are they series? Because they are only shared at 1 point. They are only connected to 1 point. So R thevening is R1 plus R equivalent 2, which gives me 343.75 ohms. So I'm done with the R equivalent. Now I have to find B thevening. I have to place back the source because I cannot find a voltage if I don't have a voltage connected to the circuit. Again, right here, I know that my B thevening is the difference between voltage 3 and voltage 4. So difference between 3 and 4. So what do I have to do? I have to find B3 using just a simple voltage divider. I find the B3 7.5, and then I find B4 using another voltage divider that is 6.87. I plug them in, I subtract them, and I get 625 millivolts. So then I draw my thevening equivalent circuit, B thevening, R thevening, and RL. I place back the RL, and I said that my R thevening is 343 as I found it. RL is 150 because it was given to me. B thevening is 625 millivolts. Now I can find the current to be 127 milliamps. I found the current because in the way they solve it, they give us this ugly equivalent, which is worse than the original, I feel like. And then they say you can use superposition to actually find the current load. So yes, you can use superposition, but we haven't learned superposition, so that's why I just wanted to walk you through the simple steps so that you can see, and the answer is the same, 127 milliamps compared to 127 milliamps that they do if doing superposition. So let's stop right here.